Hey guys, Mr. Backerberg here. In this video, we're going to take a look at differential equations. So, any equation that involves a derivative is called a differential equation. And the order of a differential equation is the order of the highest derivative that's involved in the equation. Now, we're just going to be dealing with first order differential equations. So, just an equation that has a first derivative in it. But if you move into more advanced calculuses, then you might have to deal with differential equations of higher orders, second derivatives, third derivatives, those kinds of things. So in this example, we're going to look at solving a differential equation. So we're going to find all the functions y that satisfy the derivative of y with respect to x as being secant squared of x plus 2x plus 5. So what's happened is that we started with some y equation and somebody did the derivative of that y equation and they got this differential equation. We want to work backwards to figure out what that original y equation was. Well, to turn this derivative equation into a regular y equation, to undo the derivative, we have to integrate this. So when we do the integral of this dy dx, that turns into a regular y equals. But then on the right-hand side, we have all of this addition happening. And our properties of integrals say that if you've got a bunch of addition happening when you're doing an integral, you're allowed to integrate each piece individually and then just keep the addition or subtraction in between those. So if we do the integral of this secant squared of x, that's going to turn into the tangent of x, plus if we do the integral of this 2x, that's going to turn into x squared. And if we do the integral of this 5, that's going to turn into 5x. Now, one thing that we haven't considered before as we've been doing our integrals is there might be some constant value being added on the end here. We wouldn't know if there was a constant because when you differentiate a constant, it just turns into 0. So there could be some hidden 0 on the back end of here that we wouldn't know about. And when we do the integral of 0, that's going to turn into just some general constant. And we're just going to call that constant c because we don't know what that constant is. Every single constant derives into 0. So when we integrate that hidden 0 on the end, we don't know what the constant was that turned it into 0, so we just account for that constant value by putting this plus c on the back end. Now this is called a general solution to the differential equation. We can find unique solutions to a differential equation, but we need a little bit more information in order to do that. So if the general solution to a first-order differential equation is continuous, the only additional information we need in order to find a unique solution is a single point. And we're going to call that point an initial condition. So a differential equation with an initial condition given to you is called an initial value problem. And it has a unique solution, and we call those particular solutions to the differential equation. So in this example, we're going to look at solving an initial value problem. So we're going to find the particular solution to the equation dy dx equals e to the x minus 6x squared, whose graph passes through the point 1, 0. So here we're given that initial point 1, 0. That's our initial condition. So we will have a unique solution to this differential equation. So we're going to integrate this equation so that we can get y equals, and on the right-hand side, I'm going to integrate each piece individually. So when I do the integral of e to the x, that just stays as e to the x, minus when I do the integral of 6x squared, that's going to turn into 2x cubed. But then I want to put my plus c on the back end to account for any constant that might be there. Now what we're actually going to do is solve to figure out what that constant is by using this 1, 0 point that we were given. So we're going to plug in the 1 for our x values, and we're going to plug in the 0 for our y values, and that's going to help us solve to find this constant c. So then, plugging those values in, my equation would say 0 equals e to the first power minus 2 times 1 cubed plus this c value. So on the right-hand side, e to the first power is just e. 1 cubed is 1, times 2 is 2, so this says minus 2, plus c. And we're trying to solve to get c alone. So I'm going to subtract this e over to the other side, so it becomes a negative e. and I'm going to add this 2 over to the other side. So we get a c value of negative e plus 2. So now I can take that information and plug this in for c in my integral that we got earlier. So we get the equation y equals e to the x minus 2x cubed minus e plus 2. This is our unique solution, or our particular solution, to that differential equation that we were given. Now, I mentioned earlier that we wanted our unique solution to be a continuous curve, because if it is, then that one given point kind of locks the function and graph into that particular solution over the entire domain. But if we end up with a solution that's discontinuous, then the initial condition that we're given only locks that function in over the continuous chunk of the curve that passes through that specified point. We don't necessarily know what's happening outside of that one individual chunk of the graph because of those discontinuities. So in this case, then we have to specify the domain of our solution. So in this example, we're going to look at how to handle a discontinuity in an initial value problem. So we're going to find the particular solution to the differential equation dy dx equals x minus secant squared of x using the initial condition that y is 3 when x is 0. Or we could think about that as the ordered pair 0, 3. So to find the general solution, we're going to have to integrate this differential equation. So we're going to get y equals, when we do the integral of x, that's going to turn into x squared over 2. And then minus, when we do the integral of that secant squared of x, that's going to turn into the tangent of x. But then we have to put our plus c on the back end to account for any constants that might be there. Now we're going to solve to figure out what that constant is going to be using that 0.03. So I'm going to plug in the 3 and the 0. So we get 3 equals 0 squared over 2 minus the tangent of 0 plus c. 0 squared is 0, divided by 2 is still 0. The tangent of 0 is 0. So we really get 3 as our c value. So then the particular solution, if we plug that 3 in for our c, we're going to get y equals x squared over 2 minus the tangent of x plus 3. But if we were to graph this equation out, because of that tangent in there, tangents have a whole bunch of discontinuities in their graph. So because this piece has discontinuities, and we're going to see discontinuities along the entire function. If we were to graph this function out on our calculator, this is the picture that we would get. Now we were given the initial condition of 0, 3, which happens right here on our graph. So because of all of these discontinuities in here, the only piece of our graph that we're actually able to lock down is the piece of the graph that contains that initial condition point. So what I'm focusing on is that there's an asymptote running right here along our graph, and there's an asymptote running right here along our graph as well. Now, tangents are generally discontinuous at multiples of pi over 2, so this first asymptote on the left-hand side is happening at negative pi over 2, and this asymptote on the right-hand side is happening at positive pi over 2. So as we're looking at this particular solution, we have to restrict the domain down as to being between negative pi over 2 and positive pi over 2, because that's where our initial condition point was. That's going to be it for this video. Thanks for watching.